In this video, I'm going to talk about carrying data over an radio frequency or RF signal. You know that the RF signals presented have existed only as simple oscillations in the form of a sine wave. The frequency, amplitude, and phase have all been constant. The steady, predictable frequency is important because a receiver needs to tune to a known frequency to find the signal in the first place. This basic RF signal is called a carrier signal. As you can see here, this is the carrier signal because it is used to carry other useful information. For example, with AM and FM radio signals, the carrier signal also transports audio signals. In a TV, the TV carrier signal have to carry both audio and video. Wireless LAN carrier signal must carry data. Okay, to add data onto the RF signal, the frequency of the original carrier signal must be preserved. Therefore, there must be some scheme of altering some characteristics of the carrier signals to distinguish a 0 bit from a 1 bit. Whatever scheme is used by the transmitter must also be used by the receiver so that the data bits can be correctly interpreted. This figure shows a carrier signal with a constant frequency, as you can see here. For example, if it is 1 second, okay, in 1 second we have, for example, a 2 cycle, okay, 1, 2, okay, and after that, as you can see here, the data bits 1001. This is the data bits, okay, 1001 or data stream are to be sent over the carrier signal. But how? One idea might be to simply use the value of each data bit to turn the carrier signal off or on. Okay, the bad idea one, this is the bad idea one, plot shows the resulting RF signal. As you can see, when we have 1, the signal is on. When we have 0, the signal is off. Again, here we have 0, the signal is off, and here we have 1, the signal is, for example, on. This is the bad idea 1. Actually, the bad idea 1 plot shows the resulting RF signal. A receiver might be able to notice when the signal is present and has an amplitude and correctly interpret 1 bits, but there is no signal to receive during 0 bits. Okay, if the signal becomes weak or is not available for some reason, the receiver will incorrectly think that a long string of 0 bits has been transmitted. This is bad. Okay, a different twist might be to transmit only the upper half of the carrier signal during a 1 bit and the lower half during a 0 bit, as you can see in the bad idea 2. When we have 1, okay, we have only the upper half, okay, and when we have 0, we have the lower half of the signal. This is the bad idea 2. This time, a portion of the signal is always available for the receiver, but the signal becomes impractical to receive because important pieces of each cycle are missing. In addition, it is very difficult to transmit RF with disjoint altering cycle. Because of that, both of these two ideas are poor idea. Such naive approach might not be successful, but they do have the right idea to alter the carrier signal in a way that indicate the information to be carried. This is known as modulation, where the carrier signal is modulated or changed according to some other sources. At the receiver, the process is reversed, demodulation. Okay, demodulation interprets the added information based on change in the carrier signal. RF modulation schemes generally have the following goals. First, carry data at a predefined rate. Second, be reasonably immune to interference and noise. And after that, be practical to transmit and receive. Due to the physical properties of an RF signal, a modulation scheme can alter only the following attributes: frequency, but only be varying slightly above or below the carrier frequency; phase, and also amplitude. The modulation techniques require some amount of bandwidth centered on the carrier frequency. This additional bandwidth is partly due to the rate of the data being carried and partly due to the overhead from encoding the data and manipulating the carrier signal. If the data has a relatively low bit rate, such as an audio signal carried over AM or FM radio, the modulation can be straightforward and requires little extra bandwidth, and because of that, such signals are called narrowband transmissions. In contrast, wireless LANs must carry data at high bitrate, requiring more bandwidth for modulation. The end result is that the data being sent is spread out across a range of frequencies. This is known as a spread spectrum. At the physical layer, wireless LANs can be broken down into the following three spread spectrum categories, which are discussed in subsequent sections in this video. First, frequency hopping spread spectrum, or FHSS. Second, direct sequence spread spectrum, or DSSS. And finally, orthogonal frequency division multiplexing, or OFDM. Alright, now let me to explain a little about the frequency hopping spread spectrum, or FHSS. Early wireless LAN technology took a novel approach as a compromise between avoiding RF interference and needing complex modulation. The wireless band was divided into 79 channels or fewer, with each channel being 1 MHz wide. To avoid narrowband interference, where an interfering signal would affect only a few channels at a time, transmission would need to continuously hop between frequencies all across the band. This is known as frequency hopping spread spectrum. This figure shows an example of how the FHSS technique works, where the sequence begins on channel 2, then moves to channel 25, then 64, then 10, then 45, and so on, through an entire predetermined sequence before operating again. Hopping between channels has to occur at regular intervals so that the transmitter and receiver can stay synchronized. In addition, the hopping order must be worked out in advance so that the receiver can always tune to the correct frequency in use at any given time. Whatever advantage FHSS gained avoiding interference was lost, because of the following limitation: narrow 1 MHz channel bandwidth, limiting the data rate to 1 or 2 megabit per second, and multiple transmission in the area could eventually collide and interfere with each other on the same channel. As a result, FHSS fell out of favor and was replaced by another more robust and scalable spread spectrum approach, DSSS. Even though FHSS is rarely used now, you should be familiar with it and its place in the evolution of wireless LAN technologies. About the DSSS, direct sequence spread spectrum uses a small number of fixed wide channels that can support complex modulation schemes and somewhat scalable data rates. Each channel is 22 MHz wide, a much wider bandwidth compared with the maximum supported 11 megabit per second data rate, but wide enough to augment the data by spreading it out and making it more resilient to disruption. In the 2.4 GHz band, where DSSS is used, there are 14 possible channels, but only 3 of them that do not overlap. This figure shows how channel 1, 6, and 11 are normally used. As you can see here, we have multiple channels, 1, 2, 3 to, for example, 11, and also more to 14. And here, as you can see, because each channel has a 5 megahertz bandwidth actually, or the 5 megahertz widths. Here in each channel in the DSSS method, we need 22 megahertz wide. It means that a little more than 4 channel. Because of that, here you can see when you use the channel 1, and means the signal center is residing in the 2.412 means channel 1, and here we have 11 megahertz, here we have 11 megahertz. Because of that, we can use channel 4 without any interference. Why? Because here we have 5 megahertz, here again 5 megahertz, and then 5 megahertz. Because of that, it is more than 11 megahertz we need. Then the next signal is residing, the center of the next signal is residing in the channel 6, as you can see, we don't have any interference, and in the next signal in the channel 11. Actually, when you use the 2.4 gigahertz band, you can use channel 1, channel 6, and channel 11 without any interference or disruption of the, for example,